So Reed-Muller codes, that's RM, and it's actually, I was lucky to have a nice set of collaborators. It's actually two different joint works. So the first one is with Amir Shpilka and Avi Vigdersson, and the second work that I'll talk about is with Yuval Vigdersson, who is an undergrad student at Princeton. So, sorry?
Any relation?
Yeah, a pretty direct relation. That's father and son. Father, Son, and Holy Spirit. So, okay, it seems like it's good to give some intros. So I prepared an intro quickly this morning. It's inspired by a comment from Dave Forney at the banquet last week at ITA, and by David Shea tea time remarks. So I don't have the expertise to give an historical overview of coding, so don't take, as you will see, these too rigorously. So in 48, coding is born with the paper of Shannon, and he sets the problem of capacity, and he shows you can achieve it. There exist codes with a random argument, probabilistic argument. And then lots of activity to achieve this capacity, both in the worst case and the probabilistic model, algebraic codes, and many great developments, but no good codes and for some time, and hard to get to capacity unless you allow an exponential blow up in the gap to capacity with, for example, concatenation codes. And this might be the end of the story, in fact. So there was this conference in the 1970s, which became famous because it's referred to as the Coding Theory is Dead conference. People saw that we had reached a point of diminishing return. But is that true? I think we are proof. It's not quite. So coding theory wasn't dead. It came back from the grave. And again, new ideas, lots of good people, graph-based codes. Show up with many techniques, like TCS people come and join the troops with expander codes, but still exponential blow-up, etc. But then in the 90s, message passing algorithm on the old LDPC codes of Gallagher's seem to in fact get to capacity, or at least they are very satisfying. So again, in the 90s, with this new wave, it seems like this time coding is dead. So that's the end. At least we thought so, because it came back again and adapted to new technologies and new trends. But it finally got finished properly with polar codes another 20 years after. So it's pretty recurrent, because polar codes achieve capacity, and blow-up is polynomial in the gap to capacity. If you had doubts it was dead, Venkat came with a stick and made sure it was polynomial. It was not moving anymore. So. At least, okay, you know the story. I'm a bit embarrassed to say that that's what we thought, but not quite. It's still a little bit there. These polar codes had scaling low as an exponent of 4. Random codes can get 2. So Rudy and Tom they come up with a special coupled, but it's 3. So, but there's something which is new. Instead of a new construction that maybe might be the better one and keep going, it seems like the very old Reed-Muller codes back in the 50s seem to actually achieve capacity. It might even have an exponent of 2, like random codes. So they might behave like random codes. There's still a challenge to decode them. But the funny joke is in the sense that maybe coding was dead in the 50s, but we just didn't know it. So the difficulty is to establish this claim that Reed-Muller codes achieve capacity, and also then if you can efficiently decode them. So this talk, part of it is to corroborate this claim and give some result towards that conjecture. So that's the Serpiensky matrix. I saw that name once, and I thought it was a good name for this matrix, because you see the Serpiensky triangles on the right. It's just the tensor product of the 1, 1, 0, 1. So n is the dimension if you do log n tensors. And there's both polar codes and Reed-Muller codes are obtained by you take a subset of the rows of that matrix, and then you stack them up together. And now whatever you generate from that subset of rows gives you a code. And so a question is, how do you generate a good subset of rows? So what is good? So let's first see. Oh, actually interesting. That's an old slide. Sorry about that. I forgot to skip it. So Reed-Muller codes, what they do is they look for the rows of largest weight. Okay, it's a very simple rule, very easy to parse the matrix from this. And what polar codes do, which is pretty smart, they said, okay, taking largest weight seems to make sense. For example, if you care about distance, that's the best thing to do. But if we want to achieve capacity, why don't we sort of cut corner and go for what we want, which is extract information? Because we know, in a sense, we need all the information to be extracted to be capacity achieving. So formally, if you were the talk of Telatar, you try to make the mutual information between the ith bit and the transform bit. So these are the output of the channel. The U's are the transform bit through the full squared matrix. You want to pick those rows that have these high mutual informations. One observation, if you like to think of Reed-Muller codes and try to compare them with polar codes, you can also say that by maximizing the weight, what you're trying to do is maximize the Hamming distance between the weight of the ith row to the span of the previous rows. So the high-level Reed-Muller codes are the worst case or Hamming best way of choosing the rows. You always try to push yourself from the span of the previous rows. And the other ones are the Shannon version of it. So it makes sense that these ones are going to be easier to prove to achieve capacity. But what's funny is that Reed-Muller codes, they have the best distance that you can think of as a subset of rows of this Sierpinski matrix. Why is that? It's because each time you pick a row of a given weight, you get for free all the other rows of that weight. So that's why Reed-Muller codes would be the best way to minimize the Hamming weight. But they're bad codes for the worst case model. They don't have a relative distance that is non-vanishing at the given rate, at a fixed rate. Whereas polar codes, we know they have a worse distance, but they are designed to achieve capacity. But the funny thing is that it seems like despite the fact that they are constructing for distance, they seem to also achieve capacity. And then if this is true, because they have a better distance, they might even do better performance at the finite block lengths. They will, but that's if you can do maximum likelihood decoding. If you accept that, they will have a better finite block length performance. So the goal of the talk, I'm probably already, how much time did I spend on this? 10 minutes? That was pretty long. So, sorry?
Started at 3, right? So
A little
after. So you're in about 10 minutes. You have 20 minutes left.
Okay. So the two things I want to discuss is, yes, they do achieve capacity in some regimes. I'll tell you what the regimes are. And the other is, what would be other constructions that we could think of from this matrix? So what's our measure of good? I'll discuss only the case of the binary erasure channel for this talk and maybe mention some results for errors. So a good proxy for the BEC, so this is going to be fairly basic stuff of coding. That's just the way I like to look at it. Okay, if you want to code on a BEC of parameter p, that means that you have roughly p times n random erasures in a block of length n, uniformly at random, roughly. And if you want to measure the probability of error of a given code, because of the symmetry, it's enough to look at the probability of error that you have if you send the all zero code word. So assume you send the all zero code word, then a bad erasure pattern that I represent with stars here is one for which there's another code word like here, which is not the zero code word that you transmitted, but such that you can cover with the erasure pattern. See, I cover all the ones here. Because if you do that, then you don't know if what you observe is all zeros, so you cannot deduce if this is a zero code word of this guy. So what does this mean? I want to translate that in terms of the parity check matrix. So here's the parity check matrix. You may wonder, why do I draw the same figure as what I was discussing before, which was a generator matrix? But for Reed-Muller codes, they are the same. It's the same actually construction. But in any case, this is just a flat matrix. The code is the null space of that matrix. So every vector you multiply on the right, that goes to 0. And we just said that we want to make sure that if we select a number of erasures, so it's like selecting columns here, I cannot cover a code word, which is exactly equivalent to say that these columns should be linearly independent. If they are linearly dependent, then you can come up with a way to do a mixture of them that goes to 0, which gives you a code word. Okay, so what is this property? What we are looking for in the worst case is the least number of columns that are linearly dependent. That's exactly the distance of the code. It's also sometimes called the girth of a matrix. Not to be confused with the girth of the code when you do the Tanner representation. This is just the rank of a matrix is the largest number of linearly independent columns, and the girth is the least number of linearly dependent columns. I'll tell you in a second why I call it girth. So now let's define the probabilistic girth, which is I'm maximizing over that parameter between 0 and 1. This is the sampling parameter for each column. So I pick each column in that matrix with probability S. And then I obtain a submatrix, the red one here, and ask what is the largest S I can have such that with high probability, when n tends to infinity, my matrix or my sequences of matrices are going to be having linearly independent columns. Okay. So supreme over S is a number between 0 and 1, and I call this the probabilistic girth. So the reason why we call it girth is that first we thought, okay, a good name for this would be probabilistic distance, because this is a distance, exactly, this is a probabilistic distance, but it's misleading because if you think of this as a probabilistic distance, it's not true that if you get half of this probabilistic distance, you can correct errors. There's an issue, it doesn't replicate from worst case to probabilistic. So let's just call it girth for now. And achieving a capacity on the BEC is just saying that the PCM, your parity check matrix of the code, should have a relative rank which is of the same order of the probabilistic girth. So this is nothing again new, it's just reorganizing things, and the message is that if you have a matrix which is it's supposed to design your code, if it has that property that you can take Pn columns uniformly at random and with high probability they are linearly independent, and if the number of rows of your matrix, which is the rank, assuming we don't take a matrix with redundant rows, is close to the number of columns you can pick, then you are high-girth. That's what we call high-girth, optimal, the best you can hope for. So what is a good matrix that achieves this high-girth property is a random uniform matrix. With high probability, you will be high-girth. And code achieves capacity on the BC if you have that high-girth property on the matrix it has for the parity check. So it's also another name for this would have been probabilistic MDS, because MDS is the worst case model, and this is, but again, it's just achieving capacity on the BSC. Okay, so now there's the question that I said I will discuss. The first is what is a good row selection to get this high-girth property? So the game is we have that Serpiensky matrix. How do you select a subset of rows so that we are high-girth? And high-girth for some ratio that is between 0 and 1 for the rank. The relative rank. And the other one is when are Reed-Muller codes high-girth? Because the point is, you see, it doesn't have to be. You can ask this problem when p is constant, in which case this is growing linear. But the exact same problem is well defined mathematically when p is not constant. When you just call this p times n a number s, s could be growing as square root of n. You have the same problem. How many can I pick close to square root of n columns so that I'm linearly independent with high probability? So that would just mean achieving capacity on the BSC whose parameter p, erasure parameter p, depends on n and goes to 0. And then you can also go to 1. So you can study these these regimes where p doesn't have to be constant. And what we will do is the following. We cannot prove that the result for a fixed p with Reed-Muller codes, but we're going to start with p that are like maybe small and then grow as long as we can actually get the result to hold. Okay, so we'll give a construction. First, I'll tell you a bit about the construction for getting high-girth matrices, which is inspired by Polar codes, and then I'll tell you what we get for Reed-Muller codes. So the first paper is on arXiv is with Yuval. It's high-girth matrices and polarization. Here is the idea. Like in Polar codes, do something similar except that there's no channel. I'm going to describe a process which is intrinsic to that matrix. There's no channel, there's no erasure or probability or BSC or anything. You look at the first I-1 rows of that matrix, pick the next row, that's a subscript I, and the other one is upper script. And I'll define this conditional rank has the probability that if you subsample Sn columns, so you pick each of them with probability S, the vector you obtain in green in the blue row is linearly independent of the previous vectors. And for the first row, you assume you have the old zero row stack up to initialize something.
Can you repeat the definition?
So you subsample Sn columns and ask what is the probability that this vector that is obtained by these guys here is linearly independent that all these vectors that you already have selected in that green matrix that is before from the red. The projection, yeah. So this is purely algebraic fact. There's no mutual information or entropy. But it turns out that this is exactly the same as the process, which is the BEC process, the mutual information of the channels that if you were to apply this transform as a code on the BEC channel. So just to see why this holds. So see, let's just look at the case of the 2x2 matrix. If you want to make sure that, remember I said for the first row you assume there's the 0, 0 on top. You want to make sure that this is linearly independent. Well, as long as you pick one guy, then you're good. So you just want to make sure you don't have this that happens, which is 2s minus s squared. And here, if you want to make sure that this is linearly independent of that, then you have to pick both. If you just pick 0 or just pick 1, then you are linearly dependent. And this will be s squared. You have to pick both. So 2s minus s squared, and s squared is the first two iteration, the first two numbers you get when you do dimension 2. If you want to apply this thing for dimension 4, the nice trick is that you just iterate those two functions here and here. So the same happens again and again like in Polar codes. And this is exactly the same that what you get for the BEC process, but you don't need this for now. Because as you can see that this is a built-in proxy to get that property of high-girth. It's a few lines to see why you get high-girth. It's like there's some computations, but that's the motivation. As a result, we get that high-core matrices are high-girth. By high-core, I mean that I make sure that I only keep the row. So, okay, I skipped something important. For people, I assume people know Polar codes. This is going to polarize this process. So if you iterate that process log n times, you get n values. These are the n conditional ranks from all these rows. And you tend to 0 or 1. So the fraction of components that are not extremal is vanishing. So now to construct a high-girth matrix, you just keep the ones that have some conditional rank, that have non-negligible. You pack them, and this gives you a high-girth matrix. For any S that you start with. So what does this tell us? See, I'm okay this time. So first of all, well, nothing new in a sense, because I just told you they were the same as the BEC process, so you get the same code construction as Polar codes. It's just a new view. I call this a high school level proof. So maybe that's for good high school student, but what I mean by high school is it doesn't mean it's trivial, but it's just linear algebra. You can construct that code by you just need to know linear dependence. So the rank and the girth, and then you can construct a code which is fully explicit. It will have low complexity, n log n. For example, on the BEC, you don't care about the decoding, and it achieves capacity. You
still need the Bruce Hayek to show polarization, right?
Bruce Hayek?
I mean, or Emmerich, tell us. Right?
Yeah.
Martingales, it's
Yeah, so no, so I would say, like I said in San Diego, in fact, sorry if you're in San Diego, there's overlap in this talk. You need the black box of Telatar, which get rid of martingales, and you just need orthogonal increments, so you can do algebra there. So you do algebra there, now you don't even need mutual information. You don't need to talk about channels. It's just purely algebraic, and that gives you something. Anyway. Maybe, so it's nothing new, except perhaps it is a bit interesting that it's a bit more general than BEC. It's an intrinsic property of the matrix, but it works for any field. You don't care that it's GF2. It even works over the reals or any arbitrary field. In fact, for example, you can use this for sparse recovery because it works on the reals. You can construct matrices that for probabilistic sparse recovery. So it's a bit more general, so maybe that's a plus. And it doesn't achieve capacity on the BEC, but it gets some rates. Oh, yeah. It also, that's for maybe polar code people, it also gives you an operational meaning to this Bhattacharya upper bound process. When we do polar codes for errors, we have this z 2z minus z square process that we play with all the time. If it's BC, this is exactly the mutual information, but or the Bhattacharya of the channels, but otherwise it's an upper bound, and this is like giving a meaning to it. It's this process, it's their conditional ranks. Okay, so that was a bit on the like polar code side, and now I'll tell you the result we have for Reed-Muller codes. That's the paper. It will be presented in stock in a couple of months. And the results first. So the notation is the usual notation, RM, RM. So what does this mean? Reed-Muller codes, you can define them the way I did here, which is through the Serpiensky matrix and keep the highest weight. But you can also look at them as evaluation of multivariate polynomials of bounded degree. So if you take the polynomials of degree at most r on m Boolean variables, so this is a linear space of polynomial of bounded degree. You evaluate them on the hypercube. So there's 2 to the m code words. There's 2 to the m possible vectors. Good. And you will get exactly the same code as the one I described before. It's the Reed-Muller codes. But this is the parameters. R for the degree and m for the number of variables.
You don't get very good rates though, right? What are the...
This is not constant rate. It's not a matter of... It's not getting good rates because it's capacity achieving. It's we are not in the regime of constant probability of error. It's not the same questions. You see the difference? It's not that you are suboptimal. This is achieving capacity. It's just that you are not in the regime where the probability of error is constant.
On the corners.
Yeah, you are. It's as if you're in the corner. But then you ask the question: are you tight? Are you achieving capacity in that regime? So there's no question that it would be great if we could get to constant rate. That's the thing we would like to do. But in the meantime, let me tell you what we could do. Is R can be little o of m. I think we have results for constant times m, but it's not exactly capacity achieving. There's a small dependency. Maybe we could get a small constant, let's say m to 1,000, for example. That could be doable. But if you want to get to constant rate regime, you need the rate has to be exactly m over 2. For example, that's rate half. So m over 3 is very different than m over 2. M over 2 is a constant rate. M over 3 is no longer a constant rate because... So we can maybe go linear in m, but not for sure to m over 2. And there's 2 capacity results here for the BC. This one is slightly less good. So what does this mean? This is small degrees. So that's that would be low SNR regime. Low SNR regime. Okay, that's lots of errors or erasures, and that's high SNR. So this is typically harder, like in coding theory. It's always harder to work at high SNR, clean channels. But there's a capacity result here. Okay, this is not a capacity result. So these are checks, means it works. This is a square root. So we can we can roughly correct a square root of the number of errors than what you could do with at capacity. So the techniques are different for the 4 results. This is the most work, in a sense, but the hardest because BSC high SNR. Here for the lowest SNR, it's based on the weight enumerator. Oh yeah, maybe some results. So surprisingly, there's very little result about capacity achieving Reed-Muller code. So if you really want to be able to back off for any epsilon or 1 minus epsilon the optimal rate and succeed, we only know this for r is equal to 1, which is just the orthogonal codes, just the first row. Yeah. And it took quite a bit of work to get the result for r is equal to 2. So when I say there's no result that say that Reed-Muller codes are capacity achieving, I should actually say there is r is equal to 2. And now we can push it to m divided by log m and here. So the techniques here is weight enumerator techniques. And then applying usual bounds from weight enumerators. And with maybe some a little bit more careful works to make the thing work with that scaling. And there we mainly use 5 minutes or 3 minutes?
3, yeah.
Okay. There we mainly use, this is extending a work, a very nice paper by Kaufman, Lovett, and Porat, where they get this a bound of this kind, except they have R here instead of dependency where L. So this is the notation here is that this is the relative weight of the code word, and it's counting how many code words you have up to that relative weight. And here we could push it from constant to m over 4 using the similar techniques. It's basically the technique that is based on proving that a polymer has a bounded degree. You can approximate it well by having a few derivatives. And then you push that. But what I want to discuss in the last 2 minutes is this one, which I think is an interesting case. And here is the picture. So that's the Reed-Muller codes for m is equal to 4. The way you can construct the square Serpiensky matrix, but with another permutation of the rows, is as follows. You put all the hypercube here, all 0 vector, all 1, 1. And now I just evaluate all monomials of first degree 1, degree 0, degree 1, degree 2, up to degree 4, maximal degree. So when you evaluate degree 1, you always get 1. x1 gives you the first row in that matrix here, in those vectors, etc. So now this, if you were to apply a permutations, you would get back Serpiensky, but it's a different way to organize it. So Reed-Muller codes, you just keep the rows up to about a given degree. Let's say 2 here, so that's that's RM 24. And now let's say that we have picked k columns, S columns already uniformly at random, and assume they are linearly independent. And I want to check that high-girth property, so I would like to control what is the probability that if I pick a new vector at random, I am in the span of the previous columns. And then we'll do an inductive argument to compute the probability that k columns are independent. So how we do this? First, what does it mean that this new column here in red is in the span of the previous column? So I put upper script R to specify that the dimension of these columns is this, right? The sum I is equal to 0 up to R of m choose I. So it's roughly like if R is a constant, this is like m to the R. So it's R. So the first idea, the goal is to use the intuition from polynomials. This is not just an arbitrary matrix, they are evaluation of polynomials. So being in the span, so I'm adding those guys as being the span, means the following. If you would like to express this property here, that you are in a span, as only a probability that depends on those evaluation points. Not the vectors, but the points that you are hitting in the sort of pre-image. And this is what it is. Asking that the evaluation vectors are in the span is asking that those evaluation points, that the new one you're going to draw is a common zeros of all polynomials that are defined on these variables. So I'll just quickly explain this, and then we should wrap up quick. So to be in the span of these columns, it means that another way to say that you have a flat matrix and you are in the span of all these columns is the same to say that if you take a columns and multiply on the left, you have to be orthogonal to all these columns. Now, being orthogonal means that I call this the vector f. The vector f times all these columns, let's call u, r, are equal to 0, inner product. But having a vector on the left here is like picking a collection of these monomial. It's like defining a polynomial. It's not hard to see that this is exactly equivalent to say that the polynomial defined by the indicator function at the vector u is 0. So it's like evaluating this polynomial at u. So this is what this observation is. We are asking what is the probability that we pick a new evaluation point, and it's common zeros of all these polynomials that are defined on these guys. So this brings you to trying to study how many common zeros can a set of polynomials have. And if you want to show that this set of common zeros is large, then S must be large, and you have exactly the converse result to prove that this must be so small, right? Because if S must be large, then you can have an argument. If you have too many S, then this guy must be small by the converse argument. So how do we show that the set of common zeros is large when you have enough polynomials at the beginning? Well, then the next idea is to show that if you have enough vectors in the hypercube, then you can, up to some linear transformation, map them into a Hamming ball. So why do we care about the Hamming ball? I'll not explain how we get the Hamming ball. Well, look at, this is the Hamming ball, for example, here, the up to weight of 2. So there's all vector of weight 1 and all vectors of weight 2. If you look at the evaluation of this Hamming ball, you get the identity matrix here and the identity matrix here. That's pretty easy to check, is Hamming ball maps directly to identity matrices. So these vectors are all linearly independent because of this property that the identity matrices are back there. So if you have an Hamming ball, at least that simple one, then you get linearly independent vectors, which is what we want to get. The problem is that we don't necessarily have a Hamming ball at the beginning, but by having enough vector, we are forced to have at least some Hamming ball somewhere. And what is this kind of argument? It's hashing. So at the end, it's a hashing argument. How do we deal with the fact that you don't have it exactly, but you have it up to linear transformation? With the fact that Reed-Muller codes are invariant under the affine groups. So there's a few steps in between, but that's the idea. So you can use either leftover hash lemma from Impalacio Levin Luby, or in fact you get a slightly tighter bound by using another paper, which is by Vey, a very nice paper that characterizes the generalized Hamming weight of Reed-Muller codes. Oh yeah, and Yuri asked me, Emmanuel, everybody talks about Reed-Muller codes, but are they even practical? So they are, because they were used in the 60s to send a picture of Mars with the Mariner 9 vessel. So that the answer is yes.
I said if they're capacity chain, people would have used them.
Yeah, you ask why don't they use them? They use them to send a picture of Mars.
Famous
Yeah, I see.
between Samsung and Apple, because Samsung patented the second order Reed-Muller code.
Yeah, it's the second order, I think. Yeah.
Apple also patented it.
And Apple was using it, and the judge wouldn't invalidate it. So actually, it's a famous thing, because then the International Trade Commission gave the right to Samsung, but then Obama overrode that.
I'm thinking I'm late, so sorry.